It looked fragile, more like a laboratory experiment than a spacecraft. Yet this odd, insect-like machine carried humanity to another world. The lunar module was unlike anything NASA had ever built. No wings, no aerodynamic shape, no return capability. Just 2 stages of pure engineering purpose. In this series, we explore how it came to life, from blueprint to touchdown, and how the world's best minds turned an impossible concept into the most successful spacecraft in history. This is the Lunar Module Engineering Saga.
Before it could land, the lunar module had to stand. The challenge of its landing gear would define everything that followed. From Long Island to Montreal, engineers fought to build legs that were light enough to fly, yet strong enough to survive the moon. Here's how they did it. Before a single human could walk upon the moon, engineers first had to give the spacecraft feet sturdy enough to stand there. In July of 1969, as Neil Armstrong guided the lunar module Eagle toward the Sea of Tranquility, a fragile machine descended in silence, balanced on 4 spidery legs reaching out into darkness. Each one carried the weight of history and the hopes of a world watching below. No landing gear had ever been designed for another world. These legs had to absorb the shock of landing, remain upright on an unknown surface, and serve as the launch pad for the crew's return. Their story is one of precision, courage, and international collaboration, a tale that reaches from New York to Quebec and ends forever in lunar dust. Landing on Earth is a problem long solved. Air resistance, drag, and parachutes help slow descent. But on the moon, there is no atmosphere, no cushion of air, no margin for error. Gravity there is only 1/6 that of Earth, about 1.62 meters per second squared, or 5.3 feet per second squared. And the surface? No one knew for sure. Would the lunar module sink into meters of dust? Would it strike buried rocks or rest on the rim of a crater? Early simulations could not answer. Engineers at Grumman Aircraft Engineering in Bethpage, New York, were working with almost no real data. They had to design legs that could survive impact velocities around 2.13 meters per second, or 7 feet per second. A slow fall by human standards, but a violent jolt for a spacecraft weighing nearly 15 metric tons, or 33,000 pounds. The legs had to spread wide enough to prevent toppling, light enough not to rob precious payload, and soft enough to absorb impact energy. In early design studies, Grumman tested everything from fixed skids to tripod supports. But computer models showed that 4 legs, each canted outward by about 15 degrees, offered the best stability on uneven terrain. That decision became the foundation of the final lunar module design and created a new problem. How could anyone build legs strong enough to hold a falling spacecraft, yet light enough to reach the moon? By 1965, Grumman had finalized its concept and opened bidding for subcontractors who could manufacture the precision hardware. Among 16 contenders, most from the United States, stood a relatively small Canadian firm from Longueuil, Quebec, called Heru Machine Parts Limited, today known as Heru DevTech. Though little known outside the aerospace community, Heru had a reputation for extraordinary machining accuracy. They specialized in aircraft landing gear, complex assemblies that demanded tight tolerances and faultless metallurgy. Grumman's evaluators quickly saw something unique in their proposal. Despite being a foreign company, Heru's capabilities stood above the rest. They were awarded the subcontract, a historic first. Their assignment was formidable. They had to take the engineers' drawings and transform them into flight-qualified metal, meeting NASA's strictest requirements. The landing gear would need to slow the spacecraft, prevent tipping, absorb impact energy, limit loads transmitted to the cabin above, and serve as a stable platform for the return to orbit. In short, the survival of each Apollo crew would depend on whether Heru's metal could perform flawlessly, the first time and only time it was ever used.
Each leg of the lunar module was an elegant balance of strength and delicacy. It consisted of a primary strut, angled outward, and a secondary strut, hinged for lateral support. Inside the primary leg sat a crushable cartridge of aluminum honeycomb designed to deform under load. When the LM struck the moon, this honeycomb core would crumple in a controlled pattern, absorbing kinetic energy that would otherwise shatter the structure. The mechanism was one-time use. Each leg could compress by as much as 64 centimeters or 25 inches during landing. Once crushed, it could never rebound or be reused. But that was acceptable. The lunar module was not meant to land twice. The entire assembly weighed roughly 45 kilograms or 100 pounds, yet had to arrest the descent of a 15-ton or 33,000-pound vehicle. To distribute weight, engineers fitted each leg with a footpad 94 centimeters wide, designed to press gently into dust rather than dig or skid. Friction within the struts posed a deadly risk. If one leg's piston seized or resisted movement, it could cause uneven compression and tip the craft. Heru engineers painstakingly machined double cylinder bearings, ensuring each axis of motion was nearly friction-free. They conducted exhaustive tests to eliminate stiction, the static friction that locks parts in place. At NASA's Langley Research Center, engineers built a massive gantry to simulate lunar gravity. Suspended from cables, full-scale LM mock-ups were swung and dropped to test their shock absorbers. High-speed cameras captured every deformation. The results were clear. The legs worked. The aluminum honeycomb crushed exactly as predicted, cushioning the lander from falls up to 3.05 meters per second or 10 feet per second. For the first time, humanity possessed a landing gear capable of touching down on another world.
In spaceflight, perfection is not optional, and Heru's engineers knew it. Working from Grumman's blueprints, they machined and assembled each strut to tolerances finer than a human hair. When one component was found to be 0.05 millimeters, 0.02 of an inch out of specification, it triggered an internal review. Though the error was microscopic, such precision mattered. A misalignment that small could channel impact loads unevenly, fracturing joints or bearings. The part was remade, and the project continued. Thermal tests soon revealed another challenge. During descent, the lunar module's descent propulsion system produced exhaust temperatures exceeding 260 degrees Celsius, 500 degrees Fahrenheit. The legs positioned below the engine bell absorbed more heat than anticipated. Heru and Grumman strengthened the insulation blankets surrounding each strut
to prevent damage or premature crushing of the honeycomb cores. Weight budgets remained relentless. Every gram trimmed from the gear meant extra fuel or tools for the astronauts. The final landing system added only a few hundred kilograms in total, yet carried the destiny of the entire mission. After flight qualification, NASA's reviewers praised the work. One report stated, "At no time did the availability of landing gear hardware jeopardize the Apollo program schedule. From Longueuil to Bethpage to Houston, the legs were ready."
Before trusting human lives to these spindly supports, NASA destroyed dozens in testing. At Langley, engineers dropped mock lunar modules onto various surfaces, packed soil, loose sand, and jagged rock, measuring impact loads and tilt angles. In slow-motion footage, the honeycomb absorbers collapse like concertinas, dissipating energy exactly as models predicted. Tilt tests proved equally crucial. The lunar module could survive a landing on slopes up to 12 degrees, beyond which the risk of toppling grew too high. Crews were trained to seek level ground during final descent, guided by radar and instinct. Back at Grumman's Bethpage facility, technicians rehearsed the deployment sequence. During launch, the legs were folded tightly against the ascent stage to fit inside the Saturn V fairing. In orbit, they had to swing out and lock into place using spring-loaded latches and pyrotechnic releases. Every hinge and pin was tested in vacuum chambers and cryogenic temperatures. A single jammed latch could strand astronauts in orbit, unable to land. By late 1968, after hundreds of successful test firings and drop sequences, NASA certified the landing gear for flight. It was ready for the moon.
Landing was only half the story. Once the crew touched down, survival depended on what lay inside. Pumps, valves, and life support systems built within walls no thicker than aluminum foil. Behind every switch and gauge, invisible systems kept two astronauts alive in a place no human was meant to stand. These were the lunar module's hidden lifelines.
The moon is an engineering nightmare. There's no air, no atmospheric pressure, no way to carry away heat by convection. The temperature swings are extreme, up to 250 degrees Fahrenheit in sunlight and minus 250 degrees in shadow. The lunar module had to survive both. Every mission to the moon began with the same challenge. Once the lunar module separated from the command module and descended toward the lunar surface, it became completely self-sufficient. No external power, no ventilation from the mothership, no backup except what it carried on board. It had to generate breathable air, control humidity, remove carbon dioxide, keep temperatures within limits, provide cooling for the astronauts' suits and for the electronics, and supply drinking water, all from a spacecraft that weighed only about 33,000 pounds when fully fueled. That task fell to one of the most advanced life support assemblies ever built, the Environmental Control Subsystem, or ECS.
The ECS was the lunar module's lungs and heart combined. It regulated the cabin atmosphere, handled pressure control, cooling, and water management. Its engineers at Hamilton Standard and Grumman had to design something that could operate flawlessly in vacuum, without gravity, and with almost no redundancy, yet failure meant death within minutes. The ECS maintained a cabin pressure of 4.8 pounds per square inch using pure oxygen. The decision to use 100% oxygen wasn't arbitrary. A mixed gas system, like nitrogen and oxygen, would have required heavy compressors and tanks, far too massive for lunar flight. But using pure oxygen at a lower pressure gave the same partial pressure of O2 that humans experience at sea level on Earth, while cutting weight dramatically. 2 oxygen tanks in the descent stage stored about 48 pounds of oxygen, and 2 more in the ascent stage carried another 37 pounds. That oxygen did triple duty: breathing gas, pressurization for the water tanks, and feed for the astronauts' suits. Inside the cabin, air circulated through a suit circuit, a closed loop of hoses and valves that connected both astronauts' pressure suits to the LM's systems. Even when they removed their helmets, the air continued circulating through the cabin, driven by small fans and controlled by regulators that could maintain the exact pressure needed to keep everything balanced. But oxygen alone wasn't enough. The crew exhaled carbon dioxide, and without a way to remove it, the cabin would become toxic within hours. To remove carbon dioxide, the LM used lithium hydroxide canisters. Air was drawn through beds of lithium hydroxide pellets, which chemically absorbed CO2 and trapped moisture. Each LM carried 2 primary canisters in the cabin and 2 backups in the ascent stage, enough to support a 3-day lunar stay. The chemical reaction was simple but life-saving. As the moist air passed through the canisters, the lithium hydroxide converted carbon dioxide into lithium carbonate and water, neutralizing the gas before it could reach dangerous levels. The same technology saved the crew of Apollo 13 when the command module system failed and the LM's canisters kept them alive for days. But under normal lunar conditions, the system worked so precisely that CO2 levels in the cabin stayed below 1% for the entire mission. Humidity was another challenge. Each astronaut's suit and the cabin itself produced moisture through exhalation and perspiration. Condensation could cause electrical shorts or fog the instruments. So the ECS included water separators and condensate traps, removing excess humidity and sending it to collection bags for disposal before repressurization.
In the lunar module, water wasn't just for drinking. It was essential to cooling. The LM carried 3 separate water systems: descent stage tanks for cooling, ascent stage tanks for drinking and suit water, and glycol water loops for thermal control. Water circulated through sublimators, small devices that rejected heat directly into space. Each sublimator used a thin, porous plate through which water slowly evaporated into vacuum, carrying heat away with it. This process required no moving parts and was self-regulating. The hotter the LM got, the more water evaporated. The lunar module carried about 35 pounds of water in the ascent stage for crew use, drinking, food preparation, and cooling for the portable life support systems when they suited up for EVAs. The descent stage carried additional water strictly for thermal control.
Drinking water was produced as a byproduct of the fuel cells in the command module, but the LM had no such system. Its water was loaded pre-flight and strictly rationed. Each astronaut was allowed roughly 2 pounds of water per day. That included both drinking and rehydrating freeze-dried meals. Wastewater was collected in bags and vented overboard, a plume of frozen ice crystals glittering outside the lunar module after every purge.
The lunar module had no generator. Once separated from the command module, every amp of electricity came from its silver-zinc batteries. In the descent stage, 2 batteries supplied 28 volts DC and could deliver about 2,300 watt-hours each. In the ascent stage, 4 smaller batteries provided another 2,200 watt-hours total. Combined, they gave the LM enough power for about 40 hours of continuous operation, plus a tight margin for surface stays and contingencies. These were not rechargeable. Once the batteries were drained, the LM was dead. There was no way to recharge them on the Moon. That meant every switch, every fan, every pump was part of a finely tuned power budget. Engineers at Grumman and NASA calculated power usage to the 10th of an amp hour. During Apollo 11, for example, the entire cabin lighting system used less electricity than a single 60-watt household bulb. The guidance computer, radar, communications, and ECS shared the same circuit, so one surge or short could cascade through the system. That's why astronauts had to manage loads manually, shutting down heaters, fans, or displays when not needed to conserve energy. When the LM's ascent engine finally fired to return to orbit, it did so using power drawn from batteries that had already been running continuously for days, a testament to careful design and tight margins.
Thermal control was among the most difficult engineering problems in the lunar module's design. In vacuum, heat has nowhere to go except by radiation. That meant the LM could quickly overheat under the sun or freeze solid in shadow. The solution was a combination of multi-layer insulation, radiators, and sublimators. The exterior gold foil, often seen in photos, wasn't actually gold. It was a composite of mylar and Kapton sheets, aluminized and coated to reflect solar radiation. Each layer was only a few thousandths of an inch thick, but stacked in up to 25 alternating layers, it formed a highly effective barrier against both heat and cold. Inside, a liquid cooling loop circulated a mixture of water and ethylene glycol through heat exchangers connected to the electronics and cabin air. When temperatures rose, excess heat was carried to the sublimators, where it was expelled into space. Unlike a radiator on Earth, sublimators worked by allowing water to freeze inside a porous metal plate. As the vacuum pulled the ice into vapor, it absorbed heat from the LM systems. This provided stable cooling with no moving parts, but only while water was available. That's why astronauts closely monitored water quantity indicators. If the sublimator ran dry, cabin temperature could rise dangerously fast.
The lunar module cabin was pressurized to 4.8 psi, held by walls barely 1/8 of an inch thick. Its internal volume was about 160 cubic feet, smaller than the inside of a modern minivan. Yet within that space, engineers managed to pack not only flight controls and navigation systems, but also all the plumbing, oxygen lines, coolant loops, and wiring needed to sustain life. Cabin temperature was maintained between 65 and 75 degrees Fahrenheit, controlled automatically by thermostats. The humidity stayed around 50%, and the CO2 concentration remained low thanks to constant airflow. It was, in every way, a small, functioning ecosystem, one that could run for 3 full days on stored resources alone. Even the astronauts' urine collection system was plumbed into the spacecraft's pressure system. Waste was stored in vented containers and expelled periodically through a valve to vacuum. Every ounce of water, every pound of oxygen, and every watt of electricity had been budgeted months in advance. The lunar module was, as one Grumman engineer said, a spacecraft that lived on a nice edge between enough and not enough.
Despite its apparent fragility, the lunar module was incredibly reliable. Critical systems like oxygen supply, pressure regulation, and cooling were all dual string, meaning that if one circuit failed, a backup could take over instantly. 2 oxygen regulators, 2 fans, 2 suit compressors, and redundant valves provided continuous operation even during failures. The electrical system was cross-tied between ascent and descent stages, allowing power to be shared if necessary. But in reality, the best protection wasn't redundancy, it was simplicity. The LM had very few moving parts. No generators, no rotating pumps for the cooling loops, and minimal complexity wherever possible. In space, every moving part was a potential point of failure, so engineers relied on physics, pressure differentials, sublimation, and chemical reactions instead of mechanical devices. That philosophy made the LM resilient enough to operate perfectly during all 6 successful lunar landings.
Now, all that engineering faced the ultimate test: descent. In 12 minutes, the lunar module would fall from orbit toward the Moon, powered by one engine that had never been fired more than once. What followed would become the most nerve-wracking landing in history. This is how the hardware made it possible.
At the center of the lunar module's descent was its brain, the Primary Guidance Navigation and Control System, or PGNCS, built by the MIT Instrumentation Laboratory. Inside a small silver box, the Apollo guidance computer, 16 kilobytes of memory controlled humanity's first landing on another world. It received data from the Inertial Measurement Unit, a gyro-stabilized platform with 3 precision accelerometers that sensed every change in motion and attitude. Together, they formed a self-contained reference frame, a local space bubble that let the LM know where it was, even when stars and Earth vanished from view. The guidance computer didn't work alone. It constantly compared its inertial data with readings from the landing radar, which measured both altitude and velocity relative to the lunar surface. Every few seconds, the computer fused both sets of data, correcting small drift errors from the inertial sensors. When Armstrong and Aldrin saw 1201 and 1202 alarms during Apollo 11's descent, it was this guidance system fighting for processing time, overloaded by radar data. Yet it never failed.
Its designers had anticipated overload recovery routines years before. From this hardware came commands: how much thrust to apply, how to gimbal the engine, when to pitch over and when to slow down. It was the orchestra conductor, guiding a 33,000-pound machine toward a surface that no one had ever touched.
To control descent, NASA needed a rocket engine unlike any before it, one that could be throttled smoothly from gentle hovering to full braking thrust. This was the Descent Propulsion System, built by TRW, later known as the Lunar Module Descent Engine, LMDE. At full power, it produced about 10,125 pounds of thrust, but could throttle down to just 1,050 pounds. The engine was pressure-fed, meaning there were no turbopumps, only helium gas forcing propellants into the combustion chamber. That made it reliable, simple, and compact, ideal for a vehicle that would never return to Earth. Its propellants were hypergolic: Aerozine 50, a 50-50 mix of hydrazine and unsymmetrical dimethylhydrazine, and nitrogen tetroxide. When they met, they ignited instantly. No spark, no ignition system. The same chemistry powered every Apollo engine, from the lunar module's attitude jets to the command module's main engine. Throttle control came from a variable area injector, a system of tiny orifices that could open and close to change fuel flow. A titanium combustion chamber with an ablative liner absorbed the blistering heat, over 5,500 degrees Fahrenheit or 3,000 degrees Celsius, and gradually eroded away during the burn. Engineers worried about vibration and combustion instability, but the Lunar Module Descent Engine performed flawlessly in all 6 lunar landings. And the engine could gimbal 6 degrees in any direction, allowing the computer to keep the vehicle upright while adjusting attitude through thrust vectoring. When more torque was needed, 16 smaller jets, the reaction control system, fired in microbursts, like fingers balancing a spinning coin.
Each lunar module carried 4 clusters of thrusters, each with 4 nozzles for a total of 16. Together, these made up the RCS, or Reaction Control System. These jets handled small rotations and translations, firing for fractions of a second under computer control or manual command. They used the same propellants as the main engine, Aerozine 50 and nitrogen tetroxide, but stored separately. Helium pressurization forced the liquids through their lines with no moving pumps, just valves and pyrotechnic switches. Each thruster produced about 100 pounds of thrust, enough to pitch, roll, or yaw the lunar module in vacuum with millisecond precision. The RCS gave the lunar module its delicate ballet-like control, balancing forces, stabilizing the vehicle during throttle changes, and maintaining attitude during the final hover and landing. The landing radar, mounted under the LM's belly, was the pilot's altimeter to another world. It fired 4 microwave beams, 1 to measure altitude, 3 to measure velocity. As the lunar module approached the moon, the radar switched modes, tilting its antenna to track both downward and ahead. Data streamed into the guidance computer every few seconds, altitude to within a few feet, velocity within a few inches per second. This was what gave Armstrong confidence that the computer's readouts matched reality. But NASA didn't rely on instruments alone. The commander could see his landing point through the landing point designator, a grid etched on the window. The computer displayed a look angle on the disk key, the crew's keyboard, and by aligning the crosshairs with a visible feature, Armstrong could manually shift the landing site. Each movement of the hand controller moved the landing point by fractions of a degree, translating to hundreds of feet on the surface. That's how he guided Eagle past the boulder field and into history.
Beneath the crew sat the descent stage, the squat, gold-wrapped lower half of the lunar module. It held the engine, propellant tanks, support trusses, and the landing gear. Its structure was cruciform, a central bay for the engine with propellant tanks on each side, 2 for fuel, 2 for oxidizer. Around the perimeter, 4 equipment bays held helium tanks, batteries, the environmental control system, and scientific payloads like the ALSEP experiments. Lightness was everything. The stage's thin aluminum structure and honeycomb panels weighed barely a ton, yet supported a fully fueled spacecraft of over 33,000 pounds. Thermal blankets of aluminized mylar and kapton wrapped the entire stage, up to 20 layers thick, to keep internal systems within safe limits from minus 250 degrees Fahrenheit in shadow to plus 250 degrees Fahrenheit in sunlight. Underneath, a titanium heat shield protected the lander from the engine's own exhaust plume, gases expanding to thousands of degrees and rebounding off the lunar surface. Tiny deflectors directed reaction control exhaust away from the lander's skin. Every detail, from the routing of the propellant lines to the position of the struts, was tested to survive one mission only, then to be left forever on the moon. The landing gear had one job: survive impact. Each of the 4 legs carried a crushable aluminum honeycomb shock absorber designed to compress up to 32 inches during touchdown. This absorbed the lunar module's kinetic energy and kept the spacecraft upright even if one leg struck a small crater first. 3 legs carried surface-sensing probes, metal rods that extended below the footpads. When a probe touched the moon, it triggered a light on the instrument panel, contact light. The commander then shut down the descent engine. One leg, number 1, had no probe to prevent an astronaut from stepping on it when exiting the LM. The landing legs were stowed against the descent stage during launch and deployed by spring action before powered descent. Each footpad was about 37 inches in diameter, large enough to prevent sinking into the regolith, but light enough to keep mass low. Their design was proof of elegant minimalism, strong, collapsible, and simple. Crafted by the Canadian company Haru Machine Parts Limited, later Haru DevTech. In the final minutes before landing, every system of the lunar module worked in harmony. The radar fed data to the computer. The computer commanded the engine. The gimbal balanced the thrust. And the RCS kept attitude rock steady as the astronauts scanned for a safe landing site. Then, contact light. Armstrong called, "Engine stop." The descent engine shut down after 12 minutes of continuous burn.
the longest throttled engine operation in spaceflight history up to that point. They had done it. A spacecraft built only for the moon had proven its worth, a triumph of human engineering and hardware perfection. The descent stage stayed behind, its engine bell and golden panels still resting silently where it landed, a monument not of marble, but of metal and ingenuity.
From the first blueprint at Grumman to the footprints in the Sea of Tranquility, the lunar module proved what human imagination and teamwork could achieve. It was fragile, inefficient, and unlike anything ever built, but it worked every time. 12 men walked on the moon, and all returned safely, carried by a machine that redefined the limits of engineering. This was the lunar module, delicate, brilliant, and unforgettable. This was Apollo's masterpiece.